All right, so today we're going to talk more about cosmology. Today is day 18. Um, so I'm going to talk about the first 3 minutes of the universe, uh, and then I'll talk about a little window at 1100,000 years, or 11,000 years. Um, uh, because there's an interesting thing. So 3 minutes, lots of interesting activity, and then kind of nothing for a couple thousand years, and then some interesting activity, and then things just kind of slowly get going. So we'll talk about the first couple minutes. So let's see where we were at. So this is where I left the slides. So I think that this is where I was. Yeah, so we had talked about the black body, and we did a little bit of math that I kind of waved my hands past, but basically, which is all right here. It's just basically some accounting. So what is a black body? A black body is the number density of photons per angle and some other stuff. But it's basically how many photons do I have in a little volume per wavelength bin. So the number density shifts by a cubed. A is the scale factor. So the number density changes like A, right? Because the whole universe is getting less dense. A expands. The wavelength shifts by A because they all get stretched out. So you just take your black body, you drop in those changes, and you're left with this. The only A you're really left with is the one inside this exponent, which doesn't cancel out with everything else. And so we just say, instead of just having this extra A in here, let's just say the temperature changes, because that's equivalent. So what we see from this is that if I start off with a black body in an expanding universe, it stays a black body, and the temperature goes down with the scale factor. So as the scale factor gets bigger, the temperature goes down. So this is a super, super handy feature. I can ask you what the temperature was 40,000 years ago, and you can tell me. Now, 40,000 years isn't very long, so it's the same as it was today, but I can ask you what the temperature was as a function of time, and you can get it for me. So this is the black body that is the universe, right? So the entire universe is this black body. And there's some galaxies and stuff in it, but they're absolutely inconsequential for the thermodynamics of the universe. Okay, so we have T goes like T. So as things cool, balances shift. So we have these kind of energy-dependent birth and death processes. I drew some of them up here. So I can have two photons that give me a proton and an antiproton. And I have two protons that give me a proton and antiproton, and they give me two photons. And this process is in thermal equilibrium. That means it goes the same rate in both directions. So it's temperature dependent, though. So the rate depends on the temperature. So if the temperature goes down below the mass of the proton, then I can't make protons anymore, right? Because the photon energy is too low. Similarly, we'll go through several things. So we have energy-dependent birth rates and energy-dependent destruction rates, and the expansion of the universe. And okay, we also have the Veen tail, which is the long tail in the black body. This is not a Gaussian. One of the things that Gaussians have is they fall off pretty fast. So the tails don't really have very much stuff in it. If I go way out in a distribution, so say I'm looking at like height distribution of penguins, if I look at way, way off into the tail of the height distribution of penguins, I'm going to find basically zero penguins that are 4 times bigger than the rest of them. So, but the black body has this really long tail. It's not a Gaussian. It has a long tail. Oh, the implicit assumption there was that penguin height is distributed like a Gaussian, and I'm willing to bet $1 that it is. This is not a Gaussian. You can see this tail. This still has appreciable power way out here, and if we keep going, there's still appreciable power. So that means that this is energy. Frequency is energy, right? So that means that we have some photons that are still real high energy. That even though the temperature looks like it's kind of low, we still have a buttload of these extra rare photons. They matter for the details. They don't matter for anything that I'm going to say. So, whoops, no, go back. Go back to where I put you. You are not there, you're there. So birth and death of what? So this is literally everything in the universe that we know about. And I mean all of it. Everything that we know exists in the universe is on this chart. Now we know that there are things that are not on this chart. Because I keep talking about dark matter, I'm going to continue talking about dark matter as if it were a thing. And I'm going to continue doing that professionally until somebody shows me that it's not a thing. But the evidence is built up that dark matter is probably a thing that's there. So that's not in here. Also, the neutrinos. There's a cool talk on the neutrino mass this afternoon if you want to go see it. This is an interesting problem. So let's talk about the standard model for a second. So what do we have in the standard model? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 particles. A weird number. So we have, and they're grouped into sections. So we have the quarks. There are 6 quarks. There's up and down, which are pretty common. There's charm and strange, which are less common, and top and bottom, which are pretty rare. You can tell how rare they are by their masses. So the up quark is 2 MeV. The down quark is 4 MeV. I don't know if you can see these numbers. Maybe I'll make it bigger. There you go. There you go. So the up quark is 2 MeV per c squared. MeV per c squared, that's a mass, right? Because EV, an electron volt, is the kinetic energy of an electron that's been accelerated over 1 volt, right? Remember that from way back in the day. I don't know when you learned that, actually. I have no idea when I learned that fact. Sometime in physics. Okay, these are 2 MeV. So now I'm going to drop the C and just say MeV, because energy is mass, right? So I've got 2 MeV and 4 MeV. The charm quark is a GeV. That's 1,000 times bigger. The strange quark is 100 times bigger than the up, or 50 times bigger. The top quark is 100,000 times bigger than the other ones, and the bottom quark is 4,000 times bigger, or is 1,000 times bigger. So these things are bigger, which means they're less common. Now why is that? Okay, you've heard, this is waving my hands pretty hard, but I'm going to do it anyway. You should have become accustomed to that at this point. So you've learned Heisenberg's uncertainty principle, right? Somewhere in modern? Right? What's Heisenberg's uncertainty principle say?
You can't know the position of the momentum at the same time.
That's right. With math?
Change in x minus change in p is less than or equal to h bar.
I think that's it too. Yeah. So this is exactly what you just said. So you can't know position and momentum at the same time. Here, let me change the camera. So I put this as a delta. I would rather write this as a sigma, where sigma is the variance, or the standard deviation. The variance, sigma squared, is the variance. Sigma is the standard deviation. So this is how broadly distributed the momentum could possibly be, or this is the error on the momentum and the position. So this is how well I understand x, and this is how well I understand momentum. And their product has to be less than this. Why is that? I'll probably show you later. It comes out of actually very simple physics. If I take a signal that has some width and some shape, say this has some variance, sigma, let's call this sigma x. If I take a Fourier transform of that, the variance of the Fourier transform is related to the variance of this by this equation. This equation is only a statement about Fourier transforms. But it has this massive amount of physics repercussions. So you can't know position and momentum at the same time. Similarly, you can't know time and energy at the same time. So the reason is that x and p are conjugate variables. You'll learn about this when you get to mechanics. Whenever you do Lagrangians in mechanics, which I think is in Mech 2, which you should all take. These two are conjugate variables. They're related to each other, and so their uncertainties are related like this. Time and energy are similarly conjugate variables, and their uncertainties are related like this. So the uncertainty in time and the uncertainty in energy are related. So if I don't know if I have a fluctuation that's large, it's not going to live for very long. That's what this comes down to. So this says if I have a total vacuum, I'll have particles show up, but not for very long. Bigger particles show up for even less long. So bigger particles are more rare. They're harder to get. They're harder to make. They don't probably live as long. The uncertainty on their lifetime is large because the mass is large. So when we make these particles, you have to have a lot of energy. So, okay, up and down make protons and neutrons. Proton is, I should be able to figure it out. So you can figure out what all the particles are made out of in the zoo of particle physics just by doing the combinatorics. So each quark has a mass, a charge, and a spin. Every particle has mass, charge, and spin. And some other properties, but those are the three important ones. And so when I added, so the charge is 2/3 of an electron charge, and the spin is 1/2. The spin of a down quark is minus 1/3 of an electron charge. So I have 2 ups and a down, then I have a charge of 1, and that's a proton. 2 downs and an up gives me a charge of 0. That's a neutron. Kind of neat. So I just switching these things. Yeah.
So the possibility of a fourth set of quarks is just so, it requires so much energy and it lasts for so little time, it's just not really possible? Or
We don't think there are any more quarks. There are probably other particles, but not these guys. So these guys form this nice compact set of things. Because there are bigger particles, the Higgs is big. So the quarks make up stuff. The quarks interact with the strong force. The leptons are lower mass, so the electron is the one you know most about, and it has a mass of 1/2 an MeV. That's a lot smaller than these guys, right? The proton mass is about a GeV. The electron mass is about an MeV. When I did this last time, a student was really quick in the audience and did the math in their head. What's the mass of a proton? I just said it.
GeV.
About a GeV. If I add up 2 ups and a down, I get 2, 4, 12 MeV. Where's the rest of the GeV? Binding energy. It's all the energy. That's where the rest of E equals mc squared comes from. The M in the proton, the mass of the proton, comes from the energy of the binding of these things, and a bunch of virtual particles that don't exist for very long. So a proton is not actually made up of 3 quarks. It's made up of 3 quarks that are probably sticking around and 1,000 other things that kind of come into existence and disappear. They're virtual particles that don't last for very long because they're all pretty big, so they don't last very long. Electrons don't have any constituent particles. They make up a lot of stuff. A muon is like a fat electron, and a tau is like an even fatter electron. So this is bigger. The tau is bigger than a proton, and they don't last very long. Mu's are also very large, and they don't last very long. Each one of the leptons has an associated neutrino that goes with it, and you'll see that these masses, they have upper limits on them, but according to the standard model, their mass is 0 because they can't couple to the Higgs boson. Let's talk about the other bosons. So we've got these other vector bosons. So we have these gauge bosons that actually carry the energy around. They carry the forces around. They're the ones that do stuff. So we have the gluon, and that glues the strong force together. It glues the quarks together. We have the photon, which mediates the electromagnetic field. So whenever you have an electromagnetic field, that's mediated by photons. The W and the Z mediate the weak interaction. And I don't really know why weak is so weak, but it gets 2 things, but it does. So my particle physics is kind of weak. So there's a W and a Z, and they're both charged and doing stuff, so they're interesting. But they have mass. The Higgs also has mass. So W and Z do the weak stuff. So that's like turning down quarks into up quarks to make neutrons into protons. That's what W and Z do. And then the Higgs gives everybody mass. So the Higgs gives everybody mass by being in the way and coupling to everybody at different strengths. Now the neutrinos don't couple to the Higgs, so the neutrinos formally have no mass, but you'll hear this afternoon if you go to the talk that we know that the neutrinos have mass. I'm not going to get into that because it's weird. So anyway, these are the particles that we've got, and I'm not going to say anything else because as interesting as it is, I will totally run out of time if I say all the cool things about this. Does anybody have any questions about the basic standard model? No, everybody good? Okay. Okay, so this is kind of how everything works. So,
Sorry,
yeah.
question. How does the neutrino mass affect the standard model?
Well,
Whether it has it or not?
so it means that the standard model isn't all the way right. So it means that we're missing something because we need to have a mechanism, and the standard model doesn't give us one.
Gotcha.
So that's a good question. So okay, so the first thing that happens is the protons all freeze out because they're big. The second thing that happens is the neutrinos freeze. They're little, but their cross section is also really little. So remember I was talking about energy dependent birth and death rates, so the energy dependent cross section of the neutrino is important. So higher energy neutrinos are bigger, higher energy protons are bigger, so because they have more energy. Neutrinos especially, higher energy neutrinos have a larger cross section. Let's talk about cross section for a second.
So do they have like different physical sizes based off how much energy they have?
What do you mean by physical size?
Like occupy more space? Is
That's
that like a thing,
excellent.
Or is it a point? Or is
Well, they're not points.
Okay.
They're wave functions, right? They're quantum mechanical. So they take up some space because they aren't well defined. But let's talk about the cross section of an electron for a second. So how big physically is an electron? I mean, really, really small, right? So they're, way smaller than an angstrom, right? But how does an electron run into something else? It doesn't run into it like a pool ball. It runs into it with its great big electric field. Oops. Let me draw this field right. Pointing in because it's negative. So we got this big electric field from my electron. So say I have an electron here. I'm going to define the cross section. Okay, I'm kind of waving my hands here. There are better ways to do this. I'm going to define the cross section just as the probability of hitting this atom. But or hitting this electron? But how am I going to measure that? I'm going to put, say, a foil of film over here, and I'm going to shoot particles at this, and I'm going to look at the size of the shadow. Does that make sense? And that's going to tell me how big the electron is, because that's going to tell me how things interact with it. Now, how does the size of the shadow depend on the size of the test particle that I'm shooting at my electron? Yeah.
But it's not going to be like just a hard shadow, or like it's going to be like
No, it'll be a mess. Yeah.
So how do you decide like where?
Well, I
Because
take a
you're
foil of stuff and I shoot electrons at it and I see what it does, and it turns out it does weird stuff. But let's just think for a second. I'm just going to shoot I can fix an electron, which I can't really do, but let's pretend I can. I can fix an electron, and I just shoot electrons at it. They're just going to hook around being repelled from the electric field.
Right.
There's going to be quantum mechanical interference if you really do it wrong. But let's be classical for a second. The more energy I shoot my target at with, the smaller this spot gets, because they're not going to be deflected as much. This is where I'm going with this.
Yeah.
So if I shoot really high electrons, they're just going to go like that and splat against my wall. If I have lower energy electrons, they are going to go like that and splat against my wall over here. So the cross section of this electron depends on the energy of the thing that's hitting it. Right? Does that make sense? That's true for everything. That's true for neutrinos too. Now their cross section isn't the electric field; it's the weak force, which is a little different. You don't have quite the same intuition for it, which is why I use this one. So neutrinos freeze out pretty early just because their cross-section is so low, it's hard to make them. They don't like to interact with anything. So as soon as the density gets below a lot, they stop being able to see anything, and then they freeze out. And then electron production stops. The neutron production stops basically when the protons do, but they need the neutrinos, so it's shortly after. And then the last thing that we'll talk about is neutrons, which need to be captured onto deuterium, or they decay in about 10 minutes. So the neutrons all disappear. So, nom nom nom. Okay, so protons and neutrons. So proton has a mass of a GeV. Early on, when the temperature is about 10 to the 12 Kelvin, MC squared is KT. K is the other constant. So I'm going to talk about temperature having energy multiplied by K to change the units. Temperature is an energy. And I'm going to talk about mass as energy multiplied by C squared to get that to happen. So by a temperature of 10 to the 12 Kelvin, which is about 100 MeV, the protons and the neutrons have all decoupled. And then we're left with some family of protons and neutrons. Now, I don't really know where the antimatter goes or when the antimatter goes. That's a big problem. So we're producing P and P bar. Somewhere they go away. So we're just going to pretend that they just go away and the production of protons is set. So after a few minutes, the temperature is low enough for the protons to freeze out. So by this time, which is early, so this is 10 to the 12 Kelvin. Think about what the temperature does with time. Temperature is just equal to 1 over A, right? And A, did I prove it? A goes like the square root of T. So this goes like T over the square root of time, which goes like this. Falls off like that. So it's kind of flat when you're a large time, but gets very steep very fast. So the temperature goes up very fast when in the early universe. So we start off at like 10 to the 12, which is only a minute or so after the explosion. After the protons and neutrons freeze out, that means that they're not coupled to the photon field anymore. Then they are not relativistic, so because they're so massive. Yeah.
So is there like no like large pockets of antimatter of some sort in space? It's just,
Now we'd see them.
we would see them. So there's only like normal matter out there. We haven't seen any like positrons or.
We see a lot of positrons, but there aren't like galaxies made out of antimatter.
Or like clouds of them.
Yeah, if there was a big cloud of antimatter in the galaxy, then the rest of the ISM would invade it, would push into it, and annihilate, and we'd see a huge bright spot in the gamma ray. So we would see a big cloud. So we can see positrons all the time. We can see them annihilating. And when I talk about dark matter, I'll talk about positrons again. But yeah, I think it would be really cool if the universe just fractured into positive and antimatter pockets, but it didn't do that. Yeah.
But isn't there theoretically the same amount of antimatter as there is like normal matter?
No.
No? Okay. I thought that like when it was all created, like, or create one, you have to create like.
Yeah.
Well, there's
Yeah,
random fluctuations
that's
in
true.
how much stuff-
Okay.
And then there's a giant hole in what we know, and then there's only matter.
Okay.
That's it. Unfortunately, this is one of those holes that's part of what the talk tonight is about. The talk this afternoon, he's gonna touch on the matter-antimatter asymmetry. So because neutrinos are one place where we can try to start to see where the matter-antimatter asymmetries are. So we can't see any right now. Every measurement we do on antiparticles, they do exactly the same thing that particles do. So there's physics that we're missing. I'm on the wrong slide. Okay, so neutrinos have such a small section that the cross section sets a bigger constraint than the cross section is what kills the birth and death rates of neutrinos more than the energy, because the cross section just gets so small so fast. So then the cross section, so the interaction rate gamma is the density times the cross section. Does that make sense? The density goes like a to the minus 3, which goes like t to the minus 3 halves, because why does a go like t to the 1 half when we're talking here? So remember, if we back up to our a dot over a squared equals h naught squared times omega radiation a to the minus 4 plus omega matter a to the minus 3 plus omega lambda. This is how the universe expands. When we're in the early universe, this term is really small, and this term is really small compared to this term, which goes like 1 over a. So 1 over a tiny number is a huge number. So we're in the radiation-dominated era, which means I know how a evolves. I know a goes like t to the 1 half. You'll do all this for homework. So you'll see that where that comes from again. The cross section goes like the energy squared. I don't have a homework problem for you. That's a high energy physics, which goes like t squared, which t goes like 1 over a, so that goes like 1 over a. So the interaction rate goes like t to the minus 5 halves. So when the interaction rate order of magnitude is about the same size as the expansion rate, so I'm just as likely to run into that neutrino as I am to run away from that neutrino. When that happens, we get freeze out. So we get this condition on when the neutrinos freeze out. So when when this gets less than 1, then the neutrinos freeze out. So at about a temperature of about 10 to the 10 Kelvin. So as the temperature goes down about 10 to the 9 Kelvin, when the temperature of the universe is like 5 times 10 to the 9 Kelvin, then the electrons don't have enough energy to be produced, except by, so there's some subtle details that I'm going to kind of gloss over, but basically once it gets cold enough, the electrons can't be produced, which is kind of not true, because remember I mentioned that Wien tail, which is all the like kind of extra high energy photons. Those extra special high energy photons can also make some electrons, and they go and kind of heat the CMB back up a little bit. So there's this weird thing with electrons actually being the Wien tail. But regardless, there's a bit where the energy gets pumped up, but yeah, the electrons freeze. I can't remember what I was going to say about that eta. So neutrons are complicated. So let's talk about neutrons for a second. So they mostly freeze out. They want to freeze out when the protons do, but they're in thermal equilibrium with the protons. So the protons used to be in thermal equilibrium with the photons. Then it gets too cold, and then the protons are not in equilibrium with the photons anymore, but they're in equilibrium with the neutrons. So I have this pool of electrons, protons, neutrons, and neutrinos. So we have these interactions. So I can add an electron to a proton and I get a neutron and a neutrino. I can hit a proton with an antineutrino and turn it into a neutron and a positron. Kind of awesome. Or a neutron will just decay into a proton, an electron, and an antineutrino. So we have this kind of sea of things, and all of these basically go in, this one only goes in one way because the odds of hitting all these three things together is basically 0. But all of these other two processes go both ways. So for a while, they're coupled until the neutrinos freeze out. And when the neutrinos freeze out, then I can't make I have a harder time making my protons into neutrons again. Does that make sense? So when the neutrinos freeze out, then I stop this proton. And that freezes the neutron to proton ratio at about 1/3. And then, once there are no more neutrinos making more neutrons, then they start to decay and get captured by the deuterium. So we have this neutron to proton ratio that's a third, and that's set at neutrino freeze out. And then we have deuterium. So protons and neutrons are in equilibrium with deuterium and gammas. So this one again goes both ways. So a deuteron, you can break a deuteron apart with a photon and break it into a neutron and a proton again, and then then that neutron can decay. So these processes are in equilibrium with each other. The binding energy of a deuteron is 2 MeV, and the photodissociation. So there's this Wien tail again. The photons break it up a little bit, so it's not just the mass of the deuterium that sets when the freeze-out happens. It's a little later than that because you can still break some stuff up, but you get a temperature for the deuterium of freezing out at 10 to the 8 Kelvin. Once the deuterium freezes out, we make a bunch of helium-4. So, man, I used to have a better slide here. So we have this so I thought I went through this chemistry a little better. So anyway, we've got these three populations of stuff. So you've got this eraser kind of sucks. I used to suck so bad. Remember cleaning the chalk erasers out when you were a kid? Maybe I'll just use this one's better. There. Wait, what the hell is it saying? Alright, so we've got protons, neutrons, deuterons, helium-4 and helium-3. And there's equilibrium processes between all of these guys. And they're all energy dependent. So I've got protons in equilibrium with neutrons. Neutrons in equilibrium with deuterons. I got deuterons in equilibrium with helium. We like helium-4 more than helium-3 because I can make helium-4 out of 2 deuterons, right? So all of these things are in equilibrium, and everything is getting colder, and as things get colder, different processes shut off. So there's a point at which the ratio of protons and neutrons is set, and the ratio of helium-4 is set. So you can look at the so by the end of neutron freeze out, the neutron to proton ratio is 1/7. I said 1/3 before, but some of them decayed. So if I want to see what the mass fraction is of helium to everything, does that make sense? So I just want to know how much helium to hydrogen there is, or helium to the total. That's just going to be 4 times the number of helium over 4 times the number of helium plus the number density of hydrogen. I'm just counting protons, right? Which works out to twice the neutron density over the proton density, which works out to, if you use just do a little math, this one makes more sense, a fraction of 1/4. So what this says is that, so if the neutron to proton ratio is 1/7, which is what you expect at the temperature where everything freezes out, then the helium fraction should be about 25%, and it is, and that's cool. So this was a great win for the Big Bang. So the important bit, let's get rid of that. The important bit with measuring these things is what we can tell is the temperature of freeze out, and the number density. When the helium-4 is frozen out. So we can, by looking at how much helium-4 we have to how much deuterium we have in the universe, we can measure what the baryon density was when all the helium was formed. Does that make sense? So we measure the ratio of neutrons to, so D to H, the ratio of deuterium to this one's hydrogen, tells us when and how dense. And this is baryon density. So this is the density of protons. Protons. When the helium-4 is formed. And the helium-3. So D to H tells me how dense the universe was. That tells me it this way. So this this chart shows a couple of different things. So this is baryon density. It's a theory chart, but then the squares show us measurements. So these swaths are theoretical arguments as a function of baryon density for lithium, helium-3, deuterium, and helium-4. So as the density goes up, I convert more of my deuterium to helium-4. Does that make sense? Because I can do it faster. So this one, so this equation goes faster if it's denser. So I can make more helium-4 if the universe is denser. So this green curve tells me how much helium-4 I have based on the density of the universe. So ignore the box in this blue line for a second. That's all this guy tells us. So as the density goes up, more deuterium is converted to helium. So all this D goes up here, and so that goes up with density, and deuterium goes down with density. So that's great. Now both things, so now the ratio is double sensitive because the top goes up and the bottom goes down. For helium-3 also goes down with density as it gets converted to helium-4. Lithium goes up with density. I don't understand the lithium production very well, but you'll notice, so this bar here, so okay, what did they do? They measured helium-4. So the measurement goes on the vertical axis of this. And then we read off what the baryon density of the universe was from where your measurement intersects with the theory plot. Does that make sense? So we measure that the helium-4 mass fraction is between 0.24 and 0.25, which means that the baryon density has got to be between 2 and 5 times 10 to the minus 31. Does that make sense? So that gives us the baryon density. It gives us a really tight constraint on the deuterium density. So the deuterium density is measured to be here, and that gives us this baryon density. So helium-4 and deuterium is really sensitive. The helium-3, there's not a lot of helium-3. It's hard to make. It's hard to find. It's useful. Lithium. Let's talk about lithium in a second. So D to H, the deuterium to hydrogen or deuterium to helium-4 tells us the density, and that's really useful. And this measurement is great. The lithium density doesn't really look like it lines up here very well. Maybe it does, but maybe it doesn't. So the lithium density is actually a lot lower now than what we think it should be. This is called the lithium problem, and some people over in the nuclear group are working on this. There's not enough lithium, and we don't know why. Lithium doesn't jive with the Big Bang nucleosynthesis very well. It's really easy to destroy, so it's not a huge problem. It doesn't undo all of Big Bang nucleosynthesis, but it is a shortcoming. Okay. So this gives us omega baryon. So this is omega baryon, omega B. This h squared is for our uncertainty. We can see that this is equal to 0.02. What's the relationship between this omega B and this baryon density here? These omegas are all relative to something. Yeah. So omega is just this thing divided by that critical density. So we see that the baryon density is only 0.02 of the critical density, but we know that the mass density is 0.3. So there's a lot of mass, and it isn't protons, and that's a problem. It's not electrons either. Electrons don't weigh anything. And it's not some other particle because they all decay. Like everything that isn't a proton decays eventually. So when I say that the dark matter is probably baryons, this is one of the big important measurements that are probably not baryons. This is the important measurement. So this says that the baryon density is smaller by a factor of 10, at least, than the actual total mass density of the universe. So where's all that stuff? That's dark matter. So baryon. So when we talk about dark matter, it isn't just protons that we can't see. Some of these measurements could possibly be protons that we can't see, like the rotation curve of the galaxy might be protons that we can't see, like little black holes and stuff. But this says that no, that might work, but it's not the whole answer. Even if you could solve the galaxy rotation curves with little black holes or garbage cans full of bananas or whatever, something massive, if you could do that for the rotation curve, it's not going to solve this problem. So this problem says that even if you can find some things, there's still a dark matter problem. Okay, WIMPs are weakly interacting massive particles. They're not on the standard model because they're made up stuff. So let's talk about these guys for a second. So there is a whole, you can take this standard model and tweak it a little bit and change all the leptons into the quark and the lepton behavior changes and the masses all change. The signs of the charge changes, and we get all this bizarro universe, but it basically looks the same. So each one of these particles has a supersymmetric particle that is a lot bigger. So being a lot bigger, should have erased that. Being a lot bigger, they're a lot more rare, right? So they're a lot harder to make, they're a lot harder to find. But it's not a real thing. It's a thing that you can write down. It's made up right now. So someday we might be able to find some supersymmetry, but we haven't yet, and that's what LHC was supposed to do, and it didn't show any. So maybe it's probably not there, which makes me sad because when I started this job, that was totally what was going to happen. Totally didn't pan out. So, but the WIMPs have to freeze out probably when around when the protons do. Where was I? Why massive? So we talk about weakly interacting massive particles. So each one of those, so the weakly interacting is important and massive is important. So why do they have to be massive? They have to be massive because when a particle decouples from the thermal energy, it is relativistic right away. And then the universe expands, and remember how I said the momentum goes down with A2. The protons are born close to the speed of light because they were just in equilibrium with a field of protons, right? Photons. So when the protons are all born, that means that they freeze out. They're all moving crazy, but then they all slow down with the expansion. If by the time we get to recombination, if we're too close to recombination, then when the universe recombines, then we have all of these relativistic species. And it's important that the dark matter isn't moving relativistically. I'll show you why in a minute. But basically, no, I'm not. I'm going to show you why later. But basically, the dark matter can't be moving relativistically because otherwise you can't form little galaxies. And we know we have little galaxies because it just leaves because the velocity is very high. So it has to be massive. Now this is an important chain of logic. So this is a new chalk. Thank you, chalk fairies. Relativistic, that means that their velocity is on the order of the speed of light. Or maybe it's on the order of 10% of the speed of light. It's still a lot, right? Particles are born relativistic. They cool like 1 over a. So the particle momentum goes down like 1 over a. Dark matter has to be non dark matter has to be non-relativistic at the cosmic microwave background. What do I mean by that? At the cosmic microwave background. I mean at z equals 1100 when recombination. Because after recombination, then galaxies start to form. Because hot, dark matter can't form small galaxies. Hot, dark matter can't form small galaxies. So this is why WIMPs are one of the most favored particles for the dark matter candidate, because they are massive. Being massive, it has this outcome, which is really just one process, but I pieced it out with a lot of things. So make sure that this makes sense to you. So the dark matter has to decouple in here somewhere. Why has it got to be weakly interacting? Well, I know it's not strongly interacting, or it would form stuff. It would make particles. It would make baryons. We would see it if it interacted. We would be able to have one hit the nucleus of an atom and stick there. It would stick to the nucleus. They don't do that. We can tell. We know that they don't interact with the electromagnetic force because we'd see it. That's what light is. By definition of C, we would see it. We know they do interact with gravity. The only force that's left is the weak force. Got to make them somehow, so we need the weak force to produce the particles in the first place, and that's the only way we're going to see them. So weakly interacting is important too, as is massive, even though we haven't seen them. Yeah, if dark matter were neutrinos, it would kill small galaxies. Neutrinos are always relativistic because they have basically zero mass. Let's see. So the yellow light sheet ought to see it, but it hasn't yet. And that ends the first 3 minutes of the universe. Does anybody have any questions about the first couple minutes? Yeah.
So in the beginning of the universe, there's only cold dark matter. Is that the hypothesis?
There's only cold dark matter now.
No.
At the beginning of the universe, it might be born hot, but then it cools off during the first couple minutes of the universe.
So it just has to be like cold enough that it's not like disrupting galaxies at z equals 11.
Yeah, it needs to be not relativistic by
Right.
here.
Right.
So it means it needs to be frozen out well before that, which means it's going to have to be massive. Does that make sense? So next, what happens? So after matter radiation equality happens when this term, where this term equals this term, that's matter radiation equality. After that, matter dominates, and the universe expands like t to the 3/2, not t squared to the 1/2 anymore. I mean 2/3, sorry, yeah.
What did you call it when the two terms are equal to each other?
Matter radiation equality. So after that, which happens pretty fast, I mean, you can sort it out. You can sort out when it happens. Oh, I think I do that in the homework. Ah, maybe I didn't. No, I didn't. Anyway, that's all right. So after matter radiation equality, then things just kind of cool for 1,000 years, and we get little fluctuations. There's little ripples, but they're not very big. Those ripples matter. But eventually, the electrons. Right. So eventually, electrons recombine with protons, and by recombine, I mean just combine, because they've never been combined in the first place. We call this process recombination because that's how we understand the physics, is by taking an electron off and watching it recombine with the proton. So that's how we learn how the physics works. So we still call it recombination because it's the same physics, even though it's never happened before. So if I take a proton and electron, free electron, not associated with my proton, and it gets bound to the electron, it gives off a 13.6 eV photon, right? Which then, what's that 13.6 EV photon going to do? I got a hydrogen over here. It's going to totally ionize that hydrogen. Not just excite it, it's going to rip the electron off. So when electrons recombine, it doesn't go straight to the ground state. They combine with some high energy state, which gives off low energy photons, because the difference between a high energy state and the vacuum isn't very high. And then they cascade down through a series of steps. And this process is super interesting, and I think the book touches on it, but we don't really need to get into it too much. The important bit is that the recombination is really steep and really fast, and it happens about here. And then what happens? And then we have recombination. So yeah, so then we can see through the universe. And I'll talk about the Big Bang, or I'll talk about the CMB. I'll talk about the CMB in a second, actually. But I just want to sum up everything that I had to say. So, first there's an explosion. We don't know why, but there it is. Then around 10 to the 12 Kelvin, protons and neutrons decouple. Probably also the dark matter, but we don't know. Then neutrinos decouple, because the weak cross-section is weak. Their mass is small, but the weak cross-section is really crappy. Then the photons stop making electrons. They all annihilate, and then we have an electron population. Then the protons and the neutrons make deuterium. Photons break up the deuterium. As it gets cooler, that stops happening. Deuterium forms helium. Then we have all the helium in the universe. And this process shows us, and this is important, this process shows us that there's a lot of mass in the universe that isn't protons. And okay, I say proton to mean everything that's a baryon, everything that's got quarks in it, because I don't care about anything that isn't a proton. It's either made out of protons, proton, or it's a meson and they all decay. So protons are the only things we really care about. Then nothing happens for a while. For about 400,000 years. Oh, I might have inverted. I may have said 100,000 years when I meant a redshift of 1100. It's about 500,000 years before the recombination actually happens. It's at a redshift of 1,000. So at about a temperature of about 3,000 Kelvin, photons stop breaking up all the stuff, and the neutral hydrogen forms. Eventually, things reionize, but that's later. Eventually, stars form. That's later. Does anybody have any questions on this and what's in it and why? That'd be good. Yeah.
Do you think these hypotheses are going to change because of the JWST photos that are coming out?
None of these will change with JWST. So JWST is seeing, this is all kind of clean science. This is stuff that you can write it down and it makes sense and it comes out of first principles. And it all works really well. JWST is probing after stars start to form and it gets really messy and it's all determined by the chaos of things. JWST definitely. So the CMB is really pretty well characterized, and we can see it pretty well. But it's the stuff that happens shortly after the CMB where things get weird. That JWST will help with. Okay, I got 20 minutes left. Let me talk about the CMB for a minute. I forgot. Bear with me for a second. I forgot to put those slides. I think they're here. Well, there it is. Bear with me 1 second. I forgot what's in this slide deck. Oh, yeah. Okay. Oh, I don't actually want to do it that way. I just want to. There you go. Okay. Have you guys dealt with Fourier transforms much at all? No. So okay. The Fourier transform is one of the most important things that human beings have ever done. The Fourier transform is more important than antibiotics. We die less, but the Fourier transform underpins basically all of the physics. Everything comes from the Fourier transform. Everything that we understand is underpinned by Fourier transforms. So while it seems like a cool thing, it has very deep and fundamental importance for your understanding of science. Actually, I'm going to leave that up. We'll leave that there because that series of processes is important. So, I'm not going to make you do anything with Fourier transforms today. I might. There's a thing that I do that I have done in the past with this class that I didn't do it yet, but I might still. So we'll come back to that later. So okay. How am I going to start this? Cosine of kx. We know how that works. Goes up and down as a period of 2 pi divided by k. Right? So 1 over k is the wave number. I'm gonna accidentally say wavelength when I say k sometimes because they're super equivalent in my head. So I can talk about this thing here by saying cosine of kx, or I can say wave with k equals whatever, and that's it. I can just say I have a cosine with period k, and you can write it down, right? You don't need to see all of the individual points. You just need to know cosine and the wavelength, and you can write the thing down. All you need to know is k. You don't need the rest of the cosine function because I've already told you it's a cosine function. So you don't need all of that information. All you need is what the wavelength of this thing is. I don't need to know what the. So say I'm a guitar speaker, an amplifier. It's going to move in and out like that. So I could write down the displacement of the speaker as a function of time. That's a lot of information. Or I could just write down that I've got a wave of this size. Turns out that I've got any continuous function. And that's periodic. But there's ways around periodic. It just needs to be basically continuous. Okay. I'm not a mathematician, so Anything that I say that sounds mathematical, go talk to an actual mathematician. So basically any continuous periodic function. Now, what you actually mean, there's some more rigorous math that we can stick with this, but I'm just going to wave my hands right now. Any continuous periodic function can be written as a bunch, technical term there, of sine and cosine. Any continuous function that's periodic can be written as a bunch of sines and cosines. How do we do that? Hopefully you go through this math in great detail when you go through maybe calculus, maybe later in calculus, maybe in, I forget where you learn about Fourier transforms. So anyway, I'm going to jump straight to the full and complete way. So we know e to the I theta equals what? Cosine theta plus I sine theta. Okay, so I don't need to write down cosine and sine, just write down e. E is easier to do math with because it's stuff in the exponent. It's hard to do things with the exponent, with the arguments here, because if I multiply a cosine and a cosine, the arguments add in weird ways. But if I multiply e to the I theta times e to the I other theta, they just add in the exponent. It's so much easier. So exponentials are way easier to deal with. So I can take my function f of x and write it as another function of amplitudes of wave numbers. So I've got a bunch of cosine with this k, and a bunch of cosine with another k, and a bunch of cosines with another k, and a bunch of cosines with another k. So I need to just know how much of each k I get. Does that make sense? I don't need to know the actual positions. I just need to know how much of this wave do I get versus how much of this wave do I have. So I've got f of x, that's my function, and f hat of k, this is the amplitude that each wave vector k gets. It's an equivalent description of the function. Does that make sense? I'll show you how to get f of k in a second. F of x is the integral of dk e to the I k x f hat of k. This is relatively simple. And then the other way, if you write down the inverse, f of k is the integral of dx e to the minus I k x f of x. So I have this machine called the Fourier transform. I don't really need it too much. When I need it, I'll make you do it. But you can go between a function that's a position of spatial positions to a function that's of wave numbers in Fourier space with this transform. Or I can go back with this other transform. You could just go back and forth between the two, and all kinds of great things come out of the Fourier transform. So I'm going to show you a power spectrum. So now if I have some quantity Q of x and y, x and y, because the sky has two degrees of freedom, right? The sky is two-dimensional. This is e to the I k dot x. K and x are now both vectors. Now it's two-dimensional. Q hat of k, x and ky. Right? Then the power spectrum, P of k, is the magnitude of q times q star. No, actually just q times q star, which is both a function of k. So the power spectrum is just I square the Fourier amplitudes. So I ask, how much power do I have at different wavelengths? So let's look at one. Let's look at this, which is our favorite power spectrum. This is the cosmic microwave background. So it has a big bump here. This is as a function of multipole moment. On the top axis, that's an inverse wave number, which is 1 over theta. Sky is in theta. So this is just 1 over Just think about that 1 over x. Or angular scale, which is just related. So I just have x on the top and 1 over x on the bottom. So big scale on the right-hand side, on the left-hand side, and little scale on the right-hand side. So this is small fluctuations, and this is big fluctuations, big angular size scales. Oops, I'm in the wrong camera. Does that make sense? This tells us the size of the fluctuations. Those fluctuations are here. So I've got all of these bumps. Oh, oops, I'm running out of juice. Right? So I've got bumps that are this big. I've got a fluctuation that's this big that has a bunch of little bumps on it. I have a fluctuation that's this big that's got a bunch of little bumps on it. Right? So I've got a bunch of different bumps in my picture. So we're going to take a Fourier transform of this and then just square it and get just the size of the bump versus the amplitude of the bump versus the physical size of the bump. Does that make sense? So that's what the CMB is. So we have this biggest peak here. That is what the most common size bump is. And it has an angular scale of a little bit less than a degree. Make sense? Then I have these other overtones. Now, if I did this for, say, a trumpet, you would have one big peak. If I play a B flat with the trumpet, then I would have one big peak at B flat. Here it would be 1 over the frequency. That'd be fine because we're going to be in wave number space. But that's the same idea. So I have one big peak that shows me what the basic size of the fluctuations are. And you can kind of see it, like if you kind of get by eye, this thing is kind of a typical fluctuation. And you can see I've got fluctuations that are about that big. I got this little guy here, this little guy here, this little guy here, this little guy here. All of these dudes that are about that big, that makes up the bulk of the signal. Little fluctuations that are about a degree across. This tells us the size of the universe. Why? Not now. It tells us the size of the universe at recombination. So when recombination happened, then all the photons stream out, and different pockets of the universe are different temperatures because of the sound waves rattling around. So some of them got compressed and they're hotter, some of them are rarefied and they're colder. But the size scale of those is about this. It's about 1/2 degree because that's the size of the whole universe. That's the biggest thing that you can fit into the causal horizon of the universe is this. So this is the biggest fluctuation that you can have at that point in time. And then the next ones are overtones of that operation. So these are overtones of the ringing. And the relative strengths of these two peaks tell you how much stuff is there. Yeah.
Not really understand what this has to do with the size. Like, is it the size of the fluctuation or the size of the actual universe?
Yes, both of those things. Well, I have many universes. It's the size of the causal horizon, which you can call the size of the universe, but it's the size. So let me explain this a little better. So here is the universe. I'll draw a picture. Oh, and I want to I'm going to pick this back up. This is the CMB won't be on the midterm, and it's not on the final. I just wanted to start talking about it. I'm going to give you an incomplete description. I'm going to say this, and then I'm going to move on to what to study for. Okay, so this is the universe. Let's have time go up this way. So let's say this is the Big Bang. Photon goes this way, photon goes this way. Right? So at the CMB, this is the size of the universe. Now there's another universe right here. I mean, it's the same universe, but this bit over here is not in contact with this bit, so it doesn't count. It doesn't matter. They don't care about each other. So I have another bit over here. I have a whole other universe over here. They can't talk to this one because, I mean, you can talk to this universe here. So it's infinite, right? It's infinite, it goes everywhere. But only how far a photon goes matters, because further than that doesn't exist. I can't ever have contacted a point in space over here because I would have to travel faster than the speed of light to get there, and that doesn't make any sense. Does that make sense? So this is how big the causal horizon is. So the causal horizon is the size of the universe, but the universe is empty, it is infinite, so it's really the size that matters. This is the biggest fluctuation that I can have. So I have one patch of the universe that's like here, and I'll have, say, it'll be high here. I'll have another patch of the universe that's over here. Say I've got a compression here, and I've got a rarefaction over here, so my amplitude is a little lower here. Yeah.
So in the same like region of the universe, the causal horizon is going to increase over time because there's been more time for like the light to travel.
Yeah, that's right. So the causal horizon now is bigger than it was here. But what we measure is the causal horizon here. And that's what we can see. So it's about a degree across. So this is the size of the sky. A degree across is like the size of your thumb. Okay, the size of your thumb, if we do that. This is a bunch of degrees. So the size of your thumb is the size of one of these fluctuations. So this little orange spot here, we got a red spot with an orange spot in it. That bit can't talk to the bit right next to it because it's too far away. The distance is about a degree. And that tells you, and that's what this big peak is. This big peak tells you what the biggest thing is that you could have. And that biggest thing is the size of the causal horizon at that time in the universe. And I'll have a bunch of those, because I can see a whole bunch of these things. But that's what tells me the first big peak. The first big peak is this, how big this is. Does that make sense? Then the second big peak, I've got waves inside of this, so it'll oscillate too. These two peaks can talk to each other. This peak can't really talk to this peak very well. I mean, it can, there's the sound wave crosses the whole thing. But inside here, then we can tell what the physics is going on, because I'll have a couple of overtones, and one of them, and now I forget, let's see, hopefully I wrote it down. Oh yeah, that's good stuff. I should do that. So the first three peaks, this is the important bit, and then I'm going to stop, are the causal volumes. And I only have 4 minutes left, so I'm going to stop talking about that. If you have more questions, we'll pick up the CMB after the midterm. But I wanted to at least show you it, because it's really cool. It tells us a lot. It's just like a fingerprint of the universe. So I'm going to change gears completely. Talk about what to study. Where's my note? And I did not get a chance to make good slides. Mostly because I got distracted by supercomputers. I needed to make my supercomputer do what I wanted. Okay. So, how to study. Go through the homeworks. I'm going to give you problems that are related to what was on the homework. That's what the test is going to look like. I'm probably not going to add many things that aren't on the homework, except this bit here. Might show up, but just because I think it's important, and it didn't make it onto the homework. But go through the homeworks. That's the important thing. 2, go through the slides. If it's in the slides, I probably talked about it enough to feel like it's fair game. So anything I spend a bunch of time in class on, probably fair game. And by a bunch, I mean a substantial amount of things. I say a lot of things, and so I'm not going to put you on the hook for a thing I mentioned one time. But so go through the homeworks, go through the slides, and see what I spend time on. And if you have time, watch a couple of videos. But there's now 15 hours of videos to go through, and that's a lot. So It's not 15 hours worth of quality information. So when you go through the homeworks and you go through the slides, so I just flipped through the homeworks and I looked at these topics. So things that you should make sure that you're familiar with. And these are not, these are topics for study, not individual items. So magnitudes, that's a big topic. What things look like magnitudes? What looks like a magnitude? So there's the actual magnitude, so we have the apparent, we have the absolute, brightness is. We also talked about color, which looks like a magnitude, and we talked about distance modulus, which looks like a magnitude as well. So there's a lot of things that look like magnitudes and behave like magnitudes. Make sure you're comfortable with what they all are and what they do. I feel like I might have missed something in there, but those are the basics. To stellar properties. Make sure you go through the stars lecture. All of that stuff in my head is common knowledge that everybody knows and has known since they were in kindergarten. So make sure you go through that to brush up on stellar physics. So all of the stellar stuff that I think that you ought to know for the class is in that lecture deck. So go through that one and make sure that everything makes sense and ask questions if it does, if it doesn't. Black bodies. Know what a black body is and what it does, how to get stuff out of it, where the peak is, what the tail is, how the peak changes with temperature, how the peak changes with flavor, how the peak changes with degrees of freedom. The answer is 0 for the last two. It only depends on temperature. So make sure you know what a black body is. Make sure you know what distance modulus is. So distances. So there's a whole homework on distances. Make sure you know all of those techniques. There's a bunch of techniques in that homework deck, in that homework set. Make sure you understand all of those techniques and how they work, and make sure you can apply them to something else. So just go through the problems and say, do I really get that or not? So we talked about parallax. We talked about binaries. We talked about reddening. We talked about Cepheids. We talked about type 1A. We talked about Tully-Fisher and Faber-Jackson. Not in the same homework set, but in a different homework set, but I'm still going to ask you distant questions using those guys. One thing that is really important astrophysically is using Tully-Fisher and type 1A and Cepheids together to make sure that we really understand the distances that we're measuring and calibrating everything together. Let's see. Understand star formation properties. So there's the IMF, the star formation rate, how a single stellar population works. So there's that graph of the single stellar population evolving. Make sure you understand that because that's going to show up again. If not the midterm on the final. I like that plot. I think it's important. So, so that single stellar population plot. Oh, distributions. Think about how distributions work. We've talked a bunch about distributions, but spend a minute and think about that. We talked about physics. We talked about exponential disks. We talked about singular isothermal sphere. That's the 1/r squared business, where you get a sphere. We talked about singular isothermal spheres. We talked about virial theorem. Virial theorem derivation is pretty short. I wouldn't feel bad asking you to do it on a test because it's a pretty fast derivation once you've done it. And connects a bunch of important physics. So derive the virial theorem would not be outside of the realm of possibility. see. We talked about. We talked about. We talked about rotation curves. Both for our galaxy and for external galaxies. Talked about the Oort constants and the tangent point method, and we talked about galaxies. Talked about ellipticals. We talked about spirals. Talked about how to classify them. We talked about what's in them. We talked about what's made up, what they're made up of. What's an elliptical look like? What's a spiral look like? We talked about how galaxy properties evolve with the tuning fork, which is also evolving with time. We talked about cosmology. We talked about the expansion rate. We talked about A of t. We talked about all the omegas. We talked about birth and death in the first 3 minutes. Talked about the different eras of expansion. And we talked about Einstein de Sitter. So be familiar with Einstein de Sitter. It's a terrible model, but great pedagogically. Yeah. So that, I think that's on there. That's everything that I think might be on there. No, it's not. That is a short overview of the things that are probably going to show up. There might be something else that shows up, but that's the important bit. Go through the homeworks and make sure that you don't not only know how to do those problems, but you really internalize the process that you're working on for each one of those processes. And that should do it. I don't know how many questions, but I know how much time you got, and I know how long things take you because I ask you that all the time. So, any other questions about either of these things? Yeah.
Just equation sheet. Is there going to be like an equation sheet or?
Oh, I'm sorry. What class is this? Yes. Fill in an equation sheet. I let students have a 8.5 by 11 for this one, but not for hydro. Not for the class that I just taught. And I totally forgot to mention that. That's part of why I wanted to say something. Make your own.
Okay.
8.5 by 11 inches, not feet.
One side.
Both sides.
Both sides.
Both sides. One continuous sheet. I had one, so I talk a lot about all those tables. Oh, the tables. Go through all those tables and make sure you know how big a galaxy is. I mean, what's the mass of the Milky Way is a question that I very might ask you. What's the radius of the Milky Way? It's a question I very might ask you. So there's a bunch of tables that have like various properties. Be familiar with those, like just in general. You don't have to memorize them, of course, but you know, there's a table of galaxy masses. Have some basic idea of what the parameters for galaxy masses are. I had one student that printed up her 8.5 by 11, and then printed up all of the tables, and taped them onto her sheet. So she had this like it was like a feather. It was very cool. I told her no. But it was very, very clever. And so mostly making the equation sheet is useful for going through all the stuff, which is why I let you do it. Also, there's a lot of things to remember, and my memory is awful, so yeah.
On the equation sheet, can you define the variables or just put equation?
Oh yeah, whatever you want on that sheet. I don't care. Yeah. Whatever you think that you might need. I mean, if what you do is you write down the answer for every homework problem in microfiche, then that's a useful study skill. So, oh yeah, no magnifying glasses, and no microfiche machines. Okay, of course.
What is a microfiche machine?
Microfiche is a way to take pictures on very, very, very small film so that you can archive an entire newspaper in like this much film.
Gotcha.
And
That's
yeah,
what we got at the library.
yeah, you see them at the library, or you used to anyway.
Oh, did they get rid of that?
I don't know. They've gotten rid of a lot of stuff.
Oh, they did digitize it.
They digitized a lot of stuff, so it's easier that way. But
My vision's really bad.
I've
So
been
if I
in
take
a
it off my
library in a
glasses,